Hello, y'all, and welcome to Lesson 38, Structure 2.2.1. We're going to be going over covalent bonds. It's going to be a very long one, as you can tell by all the content here. So basically, a covalent bond is formed by electrostatic attraction between a shared pair of electrons and positively charged nuclei. We're going to talk about the octet rule and the tendency for atoms to gain a valence shell with 8 electrons. We'll be able to deduce Lewis formula of molecules and ions up to 4 electron pairs on each atom. A couple things we're going to know is that Lewis formulas will show all valence electrons, bonding and non-bonding, in a covalently bonded species. We know that electron pairs in a Lewis formula can be shown as dots, crosses, or dashes. I honestly prefer dashes a little bit because I'm lazy. And molecules containing atoms with fewer than an octet will be covered. There's only a couple examples of that. We'll also talk about organic and inorganic examples, and we'll cover that in much greater detail in a later section. So without further ado, let's go over the entirety of the intro of covalent bonds. So to do that, we're going to start with ionic bonds, which we covered last time. Ionic bonds, we know that electrons are transferred, and they are transferred to other atoms or gained or transferred between atoms. Ooh, one of the eraser transferred between atoms. And as they're transferred between atoms, ions are created, and those are attracted via electrostatic attractions. And that's our ionic bond. So what's the difference between a covalent bond? Well, covalent bonds are very specific in that electrons are shared, not transferred. So that's a big deal here. And specifically, they are shared between two nuclei. Shared between two positive nuclei. And they're always going to be positive just because they're made of protons and neutrons. And that is creating an electrostatic attraction that holds it together. So if we look at hydrogen and we bond it to a chlorine, and now I'm going to go ahead and make chlorine quite a bit bigger. And right now I'm drawing Bohr models. So chlorine, I'm going to use red for its electrons. And we have 8. Then we have 7, along with the original 2. Hydrogen has blue for its electrons. And you'll notice that we have this shared pair of electrons. And what's actually happening here is that the nuclei are pulling on those electrons. Oop, that second arrow should go all the way to here. So these electrons are being shared. I'll put that. Oh, well, I've messed up that. We'll see if I can do it again. Take 2. So we're getting this shared force where both nuclei are equally pulling, or not equally, but both nuclei are attracting the shared electrons. Both nuclei attract shared pair of electrons. It's very important that it is a shared pair. Now, something to go over is that orbitals overlap in a covalent bond. And we're going to explain that much in much greater detail in a later section, especially if you're in HL, we're going to go over that overlap very specifically. But it's important to note. So if we look at maybe a hydrogen nuclei, whoops, and another hydrogen nuclei, they actually overlap with those electrons being shared in the middle. So this is the 1s orbital and the 1s orbital, and we have what we call SS overlap here. So we'll actually direct to the overlap. So those orbitals overlap and the electrons reside in that overlap. And that's only kind of true, but it's true enough for us. So how do we actually show covalent bonds? Well, we're going to learn about Lewis formulas, which you may already know. Often they're referred to as Lewis dot diagrams. but you also may not always use dots. So we're going to use Lewis formulas. These are the most, for Lewis formulas, we need to know that most molecules, which are covalent compounds, so if it's an ionic compound, we don't call it a molecule, but covalent compounds are called molecules. Most molecules do not form lattices like ionic compounds. So we can't just represent them as two things bonded together because that doesn't, in an ionic bond, that represents everything. But in a covalent bond, they don't. They create our molecules. So when we want to show what they look like, we actually use Lewis formulas to draw them or model molecules. And Lewis formulas have a very good advantage over any other diagram because Lewis formulas specifically represent bonded and non-bonded valence electrons, which are the really key aspects of this. They show them very well. So we're going to go over a couple types of diagrams that we use, and you'll see the benefit of Lewis formulas. So we could have the Bohr diagram. You could have a structural diagram or a structural formula specifically, which we'll use more in organic chemistry, but for now, structural formula, or we could have the Lewis formula. And we've already seen a Bohr diagram. I'm actually going to copy it from up here. This guy right here is our Bohr diagram. And I'm going to do just a little bit of erasing here, mostly because I don't like these green arrows for this. And lastly there. So that's our Bohr diagram. Our structural formula is very simple. It just shows the bond and the atoms. But our Lewis formula shows the bond and the electrons. You'll notice in our Lewis formula, we have this right here, this horizontal line connecting two atoms is our bond. And we have these non-bonded pairs. We always represent electrons in pairs, which represents your up and down spin within your orbitals if you're looking at the like orbital diagram. In chlorine, this would actually be our 3s. So we're always going to be representing pairs. So our Lewis formula has a couple representations. So you can use dots, X's, or lines for electrons. And I'll show you what I mean, or you can use a combination. So with HCl, you can go like this, and those lines represent the pairs of electrons. You could go HCl and do some dots, which we've seen before, actually. So let's use X's. That's also allowed. You can even do some combination H, X, and now we can see that the one electron comes from chlorine, one from hydrogen, or you can just like say they all come from who cares and just use the same thing for all of them. It's all okay. I'm going to prefer this only because I'm lazy and lines are really quick to draw. So for this point, I'm going to be using this uh, for the rest of this video, as well as any future video. So how do we actually draw binary molecules as Lewis formulas? So I'll give you some quick instructions. Draw binary molecules. There's a couple steps, and if you memorize these steps, you can do it for any molecule, not just binary, but we start by calculate the valence electrons, the total. I mean, every valence electron from every atom. Then step two, we will draw skeletal formula. So we are going to use it uh, just to kind of give us our base. And when we draw a skeletal formula, we're going to only use single lines to connect atoms. And single lines, that's the same thing as a single covalent bond. We'll talk about other types of covalent bonds in a future section, but single covalent bonds, and that is 2 electrons. Then step 3, we will add remaining valence electrons to atoms to fulfill octet rule. Remember, everything wants 8 valence electrons. And then step 4, we're just going to check our final structure. Check final structure. This number 4 is going to be mostly useless before we get to double and triple bonds, but we still want to pay attention. So let's do a quick example. So for the example, I'm going to look at F2. This is fluorine. Fluorine is diatomic. So we're going to go through each step. Step 1, fluorine has 7 valence electrons. And we have 2 fluorines. 7 plus 7 equals 14 valence electrons. We're going to keep that in mind. Step 2, we're going to draw the skeletal structure. So F bonded to F. Done. Step 3, I'm going to use a different color. So we have our F bonded to F, and that is 2 electrons because every bond or every line actually represents 2 electrons. And we need 14 electrons. So I'm going to add another 12. So 2, 4, 6, 8, 10, 12. You'll notice that once I've added that, we have 4 pairs, which is 8 electrons here, and 4 pairs, which is 8 electrons here. If I were to highlight it, I have 2, 4, 6, 8, full octet. The other fluorine, 2, 4, 6, 8, full octet. All right. So step 4 is my check. So I look at it, I count 2, 4, 6, 8, good. 2, 4, 6, 8, good. So step 4, I say I'm good. So my final diagram looks like this. Remember, you can use dots or dashes, whatever you prefer. I like lines. Like I said, I'm lazy. So that is a completed binary molecule. You now know how to draw those diagrams. But what if we have more than 2 atoms? A lot of you know things that have more than 2 atoms. So for example, methane, CH4 is methane. This is 5 atoms. So how do we draw this? Well, we can now learn how to draw molecules with greater than 2 atoms. So for molecules with greater than 2 atoms, we need to first realize that one atom is usually central, meaning it's in the middle and connecting to the others. So we call it a central atom. So how do we figure out how to do a central atom? Well, the first thing is that the steps for drawing, drawing are the same. Awesome. So we don't need to learn a new skill set. We just have to find the central atom. So to find center, or you know what, we'll say central atom, be more clear. So we have a couple things to keep in mind. They're not necessarily steps, they're just kind of guidelines. So first off, it's usually the furthest left on periodic table. Furthest left on periodic table. And there's a big exception. It is never hydrogen. We'll see why in a moment it's never hydrogen, but just know it is never going to be hydrogen. It cannot be central. Furthermore, it is usually the atom with the lowest amount in a molecule. So for example, when we look at CH4 methane, we have 1 carbon and 4 hydrogens, so it's probably going to be carbon. But we'll continue with our guidelines. The last guideline is that it's often written first. Usually when you write a molecular formula, it's usually the first thing written. The exceptions to this are acids. Acids are an exception. There's others, but for now, you can know that acids are usually an exception, and we'll go over acids in a much, much, much later section. But really, we're just going to try and get as many of these as we can when we're doing a molecule. So let's do an example like we did before. So instead of F2, let's look at CH2Cl2. Carbon, two hydrogens, two chlorine. So let's go through our guidelines. Furthest to the left, never hydrogen. So it can't be hydrogen. And carbon is more left than chlorine on our periodic table. Just knowing my periodic table knowledge, I know it goes to carbon, which is in group 14, and chlorine, which is in group 17. So carbon is going to be that winner here. It will be further left. But let's check our other guidelines. Usually the atom with the lowest amount. There is one carbon, two hydrogen, two chlorine. So it's still definitely carbon. Often written first. Carbon's written first. And there's rules for what you write first, but we'll go over that in a later section as well. So carbon is our central atom. So step one, count the valence electrons. Carbon is 4, hydrogen is 1, hydrogen is 1, chlorine is 7, chlorine is 7. So that is a total of some quick math, 14, 15, 16, 20 valence electrons. All right, step 2, we're going to draw the skeletal structure. Now, for that, I need to know what's in the middle, and we said it's carbon. There are 4 different atoms, so we're going to bond all 4. Now, someone might say, well, which atom goes where? Can I instead put chlorine here and hydrogen here? And the answer is it doesn't matter. You can put it wherever you want. And once we learn about molecular geometry, you'll realize it doesn't matter. But until we get there, we'll just go with what we know. So step 3 is we're going to fill electrons in to get to our 20, but we're going to also fulfill the octet rule. So we're going to count what we already have. We have 2, 4, 6, 8. So we have 12 valence electrons left to add. Now, hydrogen only can have 2 electrons. We talked about that in a previous section, but hydrogen only has its s orbital. So if we look at hydrogen, the Bohr model, it has the 1s orbital, and to be full, it can have 2 electrons. And it's already got that through its bonds. So furthermore, carbon in the middle has 2, 4, 6, 8 electrons. Carbon is happy. So we have 12 valence electrons. They're kind of only going on the chlorine. So let's go ahead and add them. 2, 4, 6, 8, 10, 12. All right. So that seems to be our diagram. Step 4, we're going to check it. It looks good. So that is our diagram for CH2Cl2 as written. All righty. So we've learned how to do this. We've learned how to draw different molecules. Let's learn about some exceptions. Exceptions to octet rule. So the first ones are obvious. Hydrogen and helium only have the 1s orbital. So they have 2 electrons. They fulfill what we call the duet rule, which you don't actually have to know, but having only 2 valence electrons makes them happy. Now, there's a couple other exceptions, specifically beryllium and boron. In weird cases, beryllium can covalently bond even though it's a metal, and we'll discuss that in a later section as well. But for example, in BeCl2, it will form 2 covalent bonds. Boron will never form more than 4, and almost every single exam has a question about boron being the exception to the octet rule. It likes to become boron trifluoride, this weird thing that looks a bit like this. Boron with 3 F's around it. And the quick and dirty diagram looks like that. So boron likes to not have 8, it likes to have 6 valence electrons. All right, so that is exceptions out of the way. Now we're going to move on to one of the weird cases. How do we do Lewis for polyatomic ions? We talked about polyatomic ions a little bit in the ionic compounds, and we said that they're covalently bonded compounds, but they have charges. So how do we actually do that? Well, there's a new way that we have to do things. We just have to add one rule in between, but we start the same way. We're going to calculate total valence electrons. So it seems the same, but now we're going to change it. We have to adjust value of valence electrons for charge. A polyatomic ion has a charge. If it's positive, that means we have lost electrons because losing electrons gives a positive charge. If it's negative, then we have gained electrons. A positive 2 would be 2 electrons lost, and negative 2 or 2 minus charge would be 2 electrons gained. So we're going to adjust our valence electron. Then step 3, back to what we know, determine central atom and draw skeletal formula. So we're back to doing what we know. Step 4, we're going to add remaining, remaining valence electrons to fulfill octet. Fulfill octet rule, same as before. And then we would check. So we still check step 5. We're going to check our structure. And we're going to add to step 5 later once we learn about double and triple bonds. But step 6 is also very important when we have a charge. And that's where we add square brackets over molecule and put charge in upper right. And that's outside of brackets. So let's see what this looks like. Let's do a good example of ammonium. So that's one of the ones we need to know. We need to have that memorized, NH4 plus. Now, ammonium, step 1, we're going to calculate valence electrons. Nitrogen has, not 7, nitrogen has 5, hydrogen has 1. We have 4 hydrogens, so we're going to add 4, and that's going to make 9 valence electrons. Step 2, adjust for charge. We see that here we have a positive charge. So that's going to be 9 minus 1. The positive means we've lost an electron for 8 valence electrons. All right. Step 3, we're going to determine our central atom. Well, it's got to be nitrogen because we already know that hydrogen can never be our central atom. That's the first guideline, first rule. So nitrogen is central. Step 4, we are now going to draw the skeletal structure, nitrogen and 1 bond to each hydrogen. And step 5, we're going to, I think step 3, I made a mistake. Step 3 is determine and draw skeletals. So let me erase that. Step 4 is we're going to add remaining valence electrons. Well, we already have our 2, 4, 6, 8. We have no remaining valence electrons. Awesome. So step 5, we're going to check our total valence. Oh, no remaining. Step 5, we're going to check our things. So nitrogen should have 8. It's got 2, 4, 6, 8. Perfect. Each hydrogen has 2. Perfect. So step 5, we're good. And step 6, we'll go back to purple. We're going to add brackets and put the charge in the upper right outside. So this is the diagram for ammonium, NH4 plus. It's just as easy as that. All righty. So we now know how to draw every possible thing. So let's talk about organic and inorganic. We're just going to really quickly talk about this briefly because we'll come back to it later. So molecules can be organic or inorganic. Now, that doesn't mean that we've added pesticides or not added pesticides. In chemistry, organic means contains carbon, but usually usually bonded to hydrogen. So for example, if we go all the way up to this molecule, CH2Cl2, that's organic. We have carbon bonded to hydrogen. So that's definitely an organic compound. Inorganic can have carbon, but not bonded to hydrogen. Usually, once it's bonded to hydrogen, we think about it as organic. So if you think about like diamond, that's just a bunch of carbons repeating bonded to each other. And generally, we wouldn't refer to that as organic. All right, all carbon. All right. So with organic and inorganic out of the way, let's talk about molecules bonded to itself. Molecules with one element. There's a few that we need to know, and those are our diatoms or diatomic elements. Remember, they are H2, O2, F2, I2, N2, Br2, and Cl2. Hoffman-Birkel. These are diatomic elements. They always exist in pairs. So if we refer to hydrogen, we're referring to this. If we refer to oxygen, like the oxygen in our air, it's this. If you have iodine, you always have this. Chlorine gas is that, and they always exist in these pairs unless they're bonded elsewhere. You're not going to find them alone. All right. So the last little bit of this section is let's talk about naming molecules. Because we named ionic bonds, those were super easy. You said your cation, then your anion, but we don't have cations and anions, but we name them very similarly. So we always say the atom first atom first, and name unchanged if there is one of it. And we'll talk about what I mean in just a moment. Then the second atom becomes ide. So you remember that from ionic compounds, chloride, bromide, oxide, hydride, fluoride, they all become ides. So it seems pretty similar. Here's where the difference comes in. We use prefixes to state amount of each atom. So if you have one, it is mono. If you have two, it is di. Three is tri. Four is tetra. Five is penta. Six is going to be hecta. Seven is hepta. Eight is octa. Nine is deca. And 10, oh, whoops, nine is not deca, that's 10. Nine is, whoops, nona. And 10 is deca. So how do we actually use these? The best way to learn is by doing. So let's do an example of PCl5. So the first atom, the name is unchanged if there is one of it. There is only one of it. So we're going to say this is phosphorus. And the second atom, there's five chlorines. So we're going to use five penta, pentachloride. It becomes ide. So for this molecule, PCl5, it's phosphorus pentachloride. If we have maybe one, even if we have one of each, the first one is carbon, name remains unchanged. The second one becomes monoxide. So carbon becomes monoxide. There's also a few common names. Whoops. So these are names that we use the name we have, not the scientific name. H2O, you know, is water, when really sometimes we might call it dihydrogen, two hydrogen monoxide. So H2O should be dihydrogen monoxide. We call it water. NH3, which should be nitrogen trihydride, we actually call ammonia, not ammonium, ammonia. O3, which should be trioxide, is actually called ozone. So when you think of the ozone layer, that's what we're talking about. Lastly, we have some weird name things that happen. So what if we have double vowels? Double vowels. You already saw one here. You might think back up in carbon monoxide, we might have something like monoxide, but that sounds a little weird. So we don't actually say monoxide. If we have a double O, we just convert to one O. So monoxide is what we would say. If we have an A, then an O, turns out we also still just say O. So pentoxide instead of pentaoxide. However, when we have two I's, turns out we still say the two I's. So that would become triiodide instead of triodide. It's still triiodide. We want to keep what makes it real. So there's a bunch of things to do to practice this. My suggestion is just practice as much as you can. So let's do some examples and you can try them yourself. So you can try drawing H2O. You can try drawing uh, NF3. You can try naming, let's do this. You can try naming CO2, and you can try naming, I said 2 when this should be 3, 4. So let's say draw these and name 4. Let's name N2O5. Name those guys. Give it a shot. You can pause the video now and come back when you're ready to look at the answers. So for drawing this, hydrogen cannot be the central atom. So we'll draw oxygen in the center, bonded with two hydrogens in a skeletal way. Counting the valence electrons, I have 6 and 2, so there should be 8. So I'll put them around the oxygen, and we're happy. NF3, N has 5, each fluorine has 7. That's going to be a total of 7 times 3, so that's going to be 21 plus 5. We're going to have 26 valence electrons. Nitrogen is further left, so it's going to be in the middle. Skeletally draw it with each fluorine. Then I'm going to add, so we've used 2, 4, 6 for the 3 bonds, so I need to add 20 more. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There's nitrogen trifluoride, and that's the name for it too. CO2 is your classic carbon dioxide. You exhale it, and N2O5 becomes dinitrogen pentoxide. And there you have it. So I hope this helps. I hope you know a little bit more about molecules and have a great day.